1003. Okay, that's good. Okay. So, what kind of car do you have?
90 Talon.
90 Talon.
Yes, sir.
There you go.
Awesome. Thank you.
What kind of car do you have?
96 Talon.
Yes.
FBY.
How about you? You got too many cars. I'm gonna knock your coffee over.
Thank you. Thank you.
You already got one. What kind of car you got?
NC Miata.
All right. Okay. Okay.
You got me out.
What do you got? 09. Yeah.
Yes.
What kind of car you got?
Huh?
What kind of car you got?
That runs?
Mighty Mouse.
All right. So, I'm Robert. I sell turbochargers and turbocharger accessories, a lot like Hank Hill.
Are you left-handed?
I am.
Oh, okay.
Southpaw for sure. Which is oddly enough one of the most discriminated against segments of society. In the
Yes,
day
it
of
is.
inclusion,
Mhm.
you know, you still have a desk, you still have a classroom full of right-handed desks.
Mhm.
You know, we got 4 bathrooms, but we got all right-handed desks. So, yeah. So anyway, turbos and stuff. Okay, so that's all those. These will hurt you. So.
Take some down, pass it around.
Yeah. So some DSMs, DSM, Evo, all of them. Mighty Mac truck. Yeah. Okay. Yeah. Big 4G truck. DSM. Evo 9.
NC Miata.
You're a Miata.
Yes.
And then you got one of the coolest 1Gs I've ever seen. Yeah. So DSM. So we can talk about DSMs. We can talk about a lot of things. A lot of y'all. I was going to start with like how did I come to do this? Because that's something that people kind of ask me sometimes. But a lot of you like really know me. So who doesn't know me very good? You guys, you kind of new faces to me. Yeah. Okay. Yeah, okay. So I got started doing turbochargers in around '96. I was looking for a part-time job. I'd been a machinist to put myself through school, and I needed another part-time job. I got a job at a diesel truck service place, and one of the things that we did there was Navy contracts for turbochargers for generator sets, and another part of it did in-frame overhauls on truck engines and stuff like that. And that's how I kind of got into turbos. I was really interested in turbos. I didn't want to work in just another engine machine shop or a job shop, and so I specifically sought out a turbocharger company that repaired and fixed turbochargers. So I was like, yeah, that's what I want to learn. So that's where I want to get a job. I want to get a job where I get to touch turbos all day long, because I was really into turbos. It was the mid-90s, and the idea of air-cooled Volkswagens with turbos on the back of them doing 100-foot wheelies and stuff was just the coolest thing I'd ever heard of. It was all I could think about. And one of the first turbocharger conversations I ever had was with a guy at CB Performance, which was Claude's Buggy's performance out in SoCal, and big air-cooled Volkswagen outfit. And looking back at it, I asked some of the dumbest questions that I could have ever asked when I finally got this guy on the phone. I don't remember his name was, Bill or something. And I'm telling him all this stuff, what cam I want to use, and what all this other stuff. And I thought, what kind of turbo do I need? Because you need a 60-1P trim.
Oh, yeah.
So everything I told him about what I was trying to do didn't really matter.
Yeah.
If you got an air-cooled Volkswagen, you put a 60-1P trim on it, and you're done. You go drag racing, you make 300 horsepower on an air-cooled Volkswagen with alcohol, and you have a good time. So things have come a long way since then, as far as what turbochargers are and what they can be versus what they were. But that's when I got started. Was in the '96, '97. And at the end of the 90s, we were already starting to make. I started to realize that you didn't have to build the turbocharger the way the book said the turbo was supposed to be built. You could build a turbocharger however you wanted. You could use half of this turbo and half of that turbo. You could take this turbo and change the turbine wheel in it. You could change that. You could take the compressor wheel. You could use a different cover. Oh wow, that cover's got a 3-inch outlet. I want to use that cover. And so that's how I kind of got started in it. And I'd always really liked the 1G Eclipse. They're expensive cars, and the 95, 96, those, the 1G Eclipses, those were expensive, lightly used cars at the time. technically intimidating cars at the time, you know. But they were really interesting, and so I was like, you know, that's really what I want to get involved with. It's not the air-cooled Volkswagen. So we had the air-cooled Volkswagen in storage, and we did work on DSM. So I met some guys in Oklahoma, the MDSOG or the MSDOG newsletter, you know, guys, and
Yeah.
Talent Digest and all that sort of thing. And made friends with some guys in Oklahoma, Jeff Carpenter and Chad Hogan and a bunch of other guys that were racing DSMs in Oklahoma, and a bunch of guys who are racing DSMs up here in the Northeast, because you see DSM like this, you know, the reason we have it up here in Ohio is because this is kind of where a lot of the cars got sold. This is really where the genesis of modding them was, you know, thanks to Dave. You know, Dave was a big pioneer in modifying these. Your early articles on Project Talent,
Yes.
you know, a big factor in kind of gelling all this together. So that's the late '90s, and that's like when I first started coming to the Shootout. Probably the first Shootout I ever came to. I'm not sure what year it was. I think it was probably '97, and a lot of fun. Just, you know, everybody was young. It's just to stay up all night, get up first thing in the morning, go to the track, grill burgers, drink beers, race all day. It was just good times. And the turbochargers were, you know, were my connection to all that. So a lot of fun just hybridizing them.
Yeah.
And one of the guys at the diesel truck shop that I worked with, he was like, he was a Spanish dude. He was Juan Garza was his name, and taught me so much about turbochargers when I worked with him. He was always like, man, you can't build that. Just the wrong parts. You got the wrong part numbers. You know, you're making Frankensteins. You know, you Dr. Frankenstein, man. You know, he would always call me that, and so that kind of stuck.
Your first turbos,
The, yeah, so the name kind of stuck. They were Frankensteins, so they were Frankenstein turbos, and so we did that, you know, level 1, level 2, level 3, and just kept making them bigger and bigger and bigger, and they started going faster, you know, because, you know, people were limited to 20 Gs. People were racing 16 Gs and 20 Gs at the time. So here I am, you know, 20 Gs, a 44 pound a minute compressor, and then people were running them on TDO 5H turbo wheels, the same turbo wheel that came in the 14B. So not any increase in turbine flow, but just kind of going from 32 pound a minute compressor flow to 44 pound a minute compressor flow. And he clipped the turbine to try to get some more turbine flow, which, you know, that's great. That's kind of like my size 10.5 shoe is too tight, so I'm going to put a 10.6 size shoe on. You know? So it does help turbine flow a little bit, but it really doesn't do anything, you know, good for you overall. So that everybody was running those, and guys, you had guys that were, you know, running 10s on 20 Gs and stuff, which is pretty impressive at the time, really. So we started to bump up from 44 pound a minute 20 G compressors and the factory TDO 5H turbo wheels to Garrett TO4E compressor wheels. And the TO4E compressor wheel doesn't fit into the Mitsubishi turbo. You have to change the bore diameter, you have to change the back spacing on the compressor wheel, so you have to do kind of some really precise machine work to the compressor wheel, and that's important because the compressor wheel spins really fast. So if you're going to go whittling on it, you know, you're changing the balance. So, you know, learned a lot about balancing in the process of all that. So those turbos were the Frankensteins. We would enlarge we'd take the same 7 centimeter housings that were on the 16G, and we would cut those for 6H turbo wheels, which basically takes you from, I don't know, I think like approximately a 50 millimeter exducer on the TDO 5H, maybe 48 or 50 millimeter exducer on the 5H. That's the minor diameter on the outlet of the turbine wheel. That's kind of your choke point for the turbo. Those were like 50 millimeter on the 16G and 14B. And so when we started building these Frankensteins, we were using a 6H turbo wheel, TDO 6 and 6H turbo wheel, which are like 57 and 59 millimeter exducers. So, you know, in the beginning, everybody's like, "Oh my God, it's never gonna spool. It's gonna be so lazy. It's so laggy." You know, and even Dave Busher was like, "Man, I'm not gonna run that. That's truck turbo." And I'm like, "Man, Fuso rules. You don't know. You know, truck turbos are where it's at. It's how we're gonna get more air in and out of there." Some of these too laggy. Well, eventually everybody realizes and came to love them. You know, that they really did, like, instead of peaking out around 400 wheel horsepower, you can peak out around 500 wheel horsepower. So, you know, when you come to the Shootout, you know, there were years when, you know, we had we had a lot of people, in the fastest class of the event, running our Frankensteins. It was pretty cool. It was a pretty cool era. And so those Frankenstein turbos that we were running in the late 90s were basically a kind of a nice way to make 100 more horsepower than you could with a 20G. And there were different sizes of them. We had 3 different compressor wheels and 2 different turbine wheels. Later on, we started to realize that Greddy had released an 18G for the DSM. And so we get the 18Gs for the Greddy DSM turbo, and I'm like, wait a minute, this 52020 compressor cover casting, it's got a big 3-inch inlet made onto it. I was having to take Fuso truck compressor covers and press and weld a sleeve onto the inlet of it, and to make it have a 3-inch inlet and get a nice big taper inlet on it. I was like, this is great. We need Greddy turbos. So I was trying to buy Greddy turbos. MHI was like, no, those are Greddys. And then I said, but I really want them. Eventually started selling me the castings and the 8-centimeter turbine housings. It was great because we could just take it one step further. So that gets you to right around 1999-ish. And that's when I started Force Performance at Subaru Incarnation. And it was at that point we started to realize that trying to really depend on MHI for all the parts we needed was going to be maybe not the best idea, because their idea of selling and distributing into North America was kind of like, we really don't care.
Yeah, and then the same thing was happening. It wasn't just Mitsubishi doing that. It was Garrett doing that to companies like Turbonetics, and that's why Turbonetics started casting their own parts and doing this, because you couldn't get it. The turbocharger manufacturer didn't give a crap about the competition vehicles out there and stuff at all. It was all about big diesel trucks, and
that's where the money was at, and that's what they saw, the bottom line, and performance aftermarket is really an afterthought for all these companies, really. Until recently, I have to congratulate MHI, because they've kind of come back and gone, well, we really can sell some stuff in the aftermarket if we make some good part numbers, and that led to the 18K, which is available for the Evo 9, Evo 10, and GM LTG 2-liter also for the Camaro. I don't know if you do that, but the ATS 2-liter all-wheel drive Cadillacs and the 2-liter Camaro turbos, they also get the 18K treatment. So there's a lot of possibilities there. But anyway, I'm getting off track. So in '99 we started realizing we needed to make stuff. We needed to just make our own stuff. So we made the FP30 turbine housing casting. So we made a 9-centimeter FP30 turbine housing casting. That was really popular. We rented Garrett ball bearing cartridges in those. A couple of different 30R cartridges at first, like a 52 pound a minute compressor and a 65 pound a minute compressor in those FP30 turbine housings, which was a stainless steel direct location turbo. So it fit the same DSM flange. I hadn't made this manifold at that time, but it fit the factory manifold, and a lot of people were using Evo 3 manifolds at that time because they had a different collector diameter. And so that just kind of led to us making more and more parts. So we started casting our own compressor covers. So we cloned the Greddy 3-inch inlet compressor cover and used it for years. It's real popular now. What's funny is, like, you go and look on eBay right now, and so many of the parts that are on eBay I would have loved to have had, in 2000. They're just, but they're there because we caused them to exist. And it's funny, people today will just think, well, that always existed. It was, you just used the TD06 cover with the 3-inch inlet on it. Like, but where would you get that? It only exists because we forced it to exist.
Or you just found a weird application that had it.
You had it, and then you
have to buy a whole turbo just to get a turbine housing.
We did a lot of that. We bought a lot of Cyclone Typhoon turbos and took them apart to get the shafts and stuff out of them, until we started realizing we just had to make all of our own parts. So that really led me to, instead of just building turbos, it led me towards manufacturing components, which is really the funner part of the whole thing, I think. I like building turbos, but I like seeing holes in what's available and trying to make something to fill the hole with. So we made things like the DSM race manifold was a cool product. Then we ended up making an Evo race manifold. I got both of those on sale at the booth right now for like $100 off, $150 on the DSM and $200 on the Evo 9 race manifold. And I got a pallet of them in the back of the truck, so come by if you need a manifold. But you new guys that came at the end, you got DSMs?
No.
No? Okay. So, that's okay. I was gonna give you a manifold. Who's the youngest guy with a DSM project in this room? You're on the younger side of things.
Yeah, 31.
31. Who's younger than 31 with a DSM project in here? Nobody. This is your manifold. That's your manifold. So making things, making things is turned out to be a lot of fun, and I still enjoy making things. And making things, and Tile's always been a great partner with making things because they make their own wastegates. Matter of fact, they make such a great wastegate that it's pretty much become the worldwide standard for copying a wastegate. You'll see if you see a wastegate somewhere, it's probably a copy of a Tile wastegate. It's probably not the actual Tile wastegate. It's probably a Chinese clone of Tile wastegate. But that's just testament to what a great part that was. It's such a cool part that everybody decided they wanted to make it too.
Yeah.
And
everybody takes it for granted that all wastegates were that good.
Were that good? Yeah, and they were not.
There was.
You remember the HKS wastegates? They just, you put them on the car and they're all clean and beautiful and everything. And then like 2 weeks later, it's just rusted.
Yeah. Or the Turbonetics, the Starship Enterprise thing that they had.
Yes. Oh my God.
they
Yeah.
were
With
horrible.
like it looked like it die-cast aluminum
Yes.
fins and stuff. Just terrible. So Title really changed that art of that a lot by having a focus on billet manufacturing and super alloy cap materials for their valve bodies and their valves. I mean, a lot of people don't realize that they have a foundry in Michigan where they cast all their own one-piece valves, their valve bodies, all that stuff's made in Michigan. It's pretty cool. So our partnership with Tile just got stronger over the years, and we ultimately, like you're talking about how Garrett just really doesn't care about aftermarket, generally speaking, and parts availability. We're using a lot of Garrett ball bearing cartridges, but you put 100 of these things on order with a scheduled delivery of 25 pieces a month, and you get 25 the first month, the second month you don't get anything, the third month you get 5 pieces, the fourth month you don't get anything. And then you get to the end of the PO, and then they send you like all 80 of them at one time because they got to hit the PO or else you can cancel it. So it's a scheduled delivery like that ultimately drove us to create Zona Rotor Turbocharger, because if we're going to have deliverability and lack of parts problems, I want it to be because I did it. I want it to be my mistake. I don't want to be able to blame somebody else for me not having the parts I need. So Tile and Force Performance joined together to make Zona Rotor Turbocharger, which is just really the thing I'm most proud of in my whole career so far is Zona Rotor Turbocharger. We set out to build the most perfect and top shelf turbo possible. So billet stainless steel bearing housings, patented ball bearing setup with variable preload built into it, huge water jackets. You can run these things at their rated flow rate, steady state, at their max speeds, and they'll cool. They won't fail. When we say if it's an 82 pound a minute, you can put it in an airplane. You can run it 82 pound a minute all the way from New York to California. That's a steady state rating. Drag racing, you do this for 8 seconds. You can do a lot of nasty things for 8 seconds and hold your breath and hope you get through it. But if you want to talk about steady state and thermal, temperature control, and that the previous guy, the temp control guys. What was their name?
DEI.
Yeah.
They'll tell you how important thermal control is, and managing heat is really critical. So going to higher level alloys, and better water jackets and things like that was a big part of what we wanted to do.
That's interesting. You point that out, and I had a conversation with you maybe about a year ago, and we were talking about different types of compressor wheel materials. And one of the things that you pointed out to me was that the strength of the aluminum, depending on what temperature that is amazingly different. So these guys that are going out and doing these half-mile runs, or even guys that are just hitting on it, every time they're doing that compressor wheel is getting weaker and weaker.
You stack up you stack up those BTU in that compressor wheel, and that goes back to the steady state versus burst operation. So can do a lot. You can do a lot of nasty things for a short period of time. You just hold your breath and cross your fingers and do it for 4 seconds and live through it. But steady state's a different story. And yeah, you're exactly right about compressor wheel alloys. Has anybody ever thought about how different strengths of wheels and stuff like that?
Stop. Let's get the next segment. Okay, you're good.
So I talk about compressor wheels and alloys and temperature limitations and stuff like that, if any of that's interesting. Yeah. Okay, so there's different kinds of compressor wheels, cast wheels and billet wheels. A lot of people think billet wheels are unilaterally better than cast wheels. It's not really true. And particularly today, in today's market, there are a lot of really poorly made billet wheels.
Yeah.
Because Asia came to realize that billet was the word that we needed to have on the product in order to sell it. So everything got made in a billet style. But you can have a thing that looks like the right thing and have it not be the right thing. And billet compressor wheels out of Malaysia and in China is a great example. And they'll call them the weirdest thing. They'll call them, it's a 20G, it's a billet 20G, and like, well, it's not, But so materials have a lot to do with it. You cast alloys, you can. I won't go into that. But there's ways to improve the castings hip processes for increasing the strength of aluminum castings. But if you start with the right alloy of billet aluminum, like a 2600 series alloy, you have a temperature profile that's really great up to about 300 degrees Fahrenheit, up to about 350 degrees Fahrenheit. And if you get the turbocharger heat soaked at 350 degrees Fahrenheit, like some steady state high power use, you have to realize that at 40 pounds of boost, your compressor outlet temperatures are 300 degrees Fahrenheit. Regardless of how efficient your compressor wheel is, they're at least that hot. They might be hotter if you got a poor compressor wheel. The compressor outlet temperature might be 400 degrees Fahrenheit if it's not a very good arrow on the compressor wheel. So if you run that for 8 seconds, the wheel doesn't accept all that heat. But if you just did 14 highway pulls in a row, it has accepted that heat. Okay, and so instead of the compressor wheel having its design strength, it has 40% of its design strength. Okay, so you get it heat soaked like that, and it has half of the strength that it had at room temperature, and half the strength that the engineers think it's going to have on any given day. And then you go, I actually want to spin it 10% faster than what it's rated for. Well, if you want to spin it 10% or 20% faster than what it's rated for, and you're operating it in a manner that causes it to be 25% hotter than it should be, you're just doing two things that don't fit together at all. And you see people exploding compressor wheels, and the high strength billet compressor wheels, before they explode, they'll stretch. And you can see this on turbos that people like class limit turbochargers, and that's a whole topic we can talk about their class limit class turbos. But class turbos get run only at their critical top speed because they only
beyond.
Yeah, it starts at the max rating and just goes up from there. And what they'll do typically is they'll start to stretch. And if you're servicing one that's been run really hard, you'll notice that the hole, the bore in the compressor wheel at the bottom of the wheel versus the top, it could be maybe 3 thousandths larger at the bottom than it was at the top. It didn't start off that way, okay? But you ran it so hard that you stretched it, and it'll stretch to about 8 thousandths of an inch difference in the bore at the bottom to the top. Wow. And then beyond, if you push them even beyond that, if it stays balanced through that, which it probably won't, it'll explode. Right? So we see a lot of turbos exploding these days, and the safety of exploding turbos is something I'm really concerned about. And I always caution people about it, against using aluminum downpipes and things like that, because there's really no hope of containing any of the grenade parts that are going to come out of that. So temperature has a big impact on it. So if you want to do one 8 second hit, and you got a turbocharger that's just, you've idled it for a few minutes, you got your oil temperature to 180, the turbo's probably at ambient or near ambient, maybe 150 degrees Fahrenheit, you can run it faster than you ought to and get away with it. But if they just called you back to the lanes after you just made a pass, now you've got a 250 or 300 degree turbocharger, and if you try to run it again the same way, overspeeding that you did the previous pass, you're gonna stretch it and it might blow up. why is it bad when the wheel stretches? It's all built. If it just stretches, it's just going to stay there. Everything's fine, right? No. Okay. When the compressor wheel stretches in diameter because you're spinning it so fast, you know, you ever play that game where two people hold each other and spin around in a circle? Whatever, you let go, you fly away. That's what's happening in the compressor. It's getting stretched. So when it does get stretched, you have what's called a conservation of volume problem with the wheel. So when it stretches in diameter, it also shrinks in its axial length at the same time. That shrinking in the axial length allows the compressor wheel and the nut to shift slightly, to take up that, and the threads on the wheel, the threads on the shaft are designed for keeping torque on the nut while it's under power. So if it stretches and it's on power, it's going to tighten itself again. But now the compressor wheel is rotated 20 degrees or 30 degrees, or who knows exactly. The wheel might have gone around a couple of times before the nut got tight. Okay, and so what you've got now is a turbocharger that might have been. Love that sound. It might have been balanced like to within half a G at 140,000 RPM. But once that wheel stretches and it shifts a little bit, man, it might be 2 Gs at 100,000 RPM now. So now you're trying to take it really to the red lines, really as far as you can, but it's not the same turbo it was on the previous pass. And then that's where you get your failure.
Yeah.
So that's a big problem with the compressor wheel. That's why you want to also always monitor what your wheel speed is if you think you're anywhere near the end of the compressor map. And a good way to keep an eye on it, go, well, I don't have a shaft speed sensor. Not everybody does, okay? But most turbochargers will have some sort of power rating associated with them. So anybody that sells you a turbo ought to be able to tell you what in real general terms, what the power rating of that turbocharger is. So somebody's going to sell you a 60-1 P-Trim turbo, you're going to say this is a power rating of about 550 horsepower. So if you're running it at 800 horsepower, guess what? You are way past the speed limits. Okay, you should have some intuition that will let you know that you're doing way more than it was designed to do. You don't need a tach to tell you that. You know, if you're making 600 horsepower on a 450 horsepower turbocharger, you're on borrowed time. That's the way it goes, and that kind of goes back to class racing. I really think on classes, if they want to control classes, they should limit throttle body size. You should not limit turbo. We should go to a post turbo restrictor so that we don't just keep. Somebody's going to get hurt with a turbocharger. Is the problem, and it hadn't happened that I know of that anybody's got terribly hurt, but it's just a matter of time. They people, especially in class racing, and I think the organizers of these events that have class limited turbos, I think they need to understand they're accepting some responsibility because they're encouraging it to happen. The turbocharger manufacturers are posting ratings. They're saying this is a 600 horsepower turbocharger, and the guy that's got the class, the race event, he's like, well, I need to slow these cars down. So these cars are making 800 horsepower, so I'm gonna force them to use a 600 horsepower turbo. They're still gonna make 800 horsepower, guys. They're just gonna smoke the fool out of everything. They're gonna go to methanol. They're gonna add nitro. They're gonna do whatever they can, and that turbo is just going to pop like a balloon, man, at some point or another. So class racing is you're going to really be careful of shaft speeds when you're class racing. Part of a successful turbo class limitation program is speed sensor data. And the best way to run a turbocharger in a inducer limited class is to ask the turbo supplier what is the best reliable high RPM that I can operate this turbo at, and you monitor turbo shaft speed and you do boost control so that you are at that RPM the entire time you're running the car. Well, how much boost is that? It doesn't matter.
Doesn't matter, yeah.
It really doesn't matter. That might be 60 PSI in the mid-range, it might be 20 PSI at the top end, but you gotta not go past that line.
Yeah, I think that, how much boost will this turbo make?
Get that question.
That's the worst thing. And,
Yeah.
and anybody who starts talking about performance and turbochargers your engine, and I want to be able to run 65 pounds boost. Why? Like, that's just an arbitrary number. It means nothing. If you tell me you need to make 1,000 horsepower, okay, fine. Let's figure out how to make 1,000 horsepower.
Yeah,
That's really the best setup for it.
Easiest on all the parts.
Yeah.
And that's, you package planning instead of just boost planning. And, even beyond like, hey, how much boost can this run? You get the EMAP crew these days. They're like, oh, it's too much back pressure. They'll tell you it's got too much back pressure, they haven't even measured it. But they read that on the forum that back pressure's bad, so we don't want it. But you're gonna have to have some back pressure, and that's where you're paying for your compressing at. So you do have back pressure, and you know that's another great topic is how much back pressure, 2 to 1, 1.5 to 1, 1 to 1, 0.8 to 1. On some of the real cutting edge stuff like the zone rotor stuff, we have cars that can operate at 0.7 ratio, like less EMAP than boost. We have cars that can run 40 psi boost pressure and have 33 pounds of EMAP. And that's just that comes down to project planning and power planning. Where are we at time-wise?
Well, we're good because we don't have any. I mean, if you want to keep going, if you
Okay.
have questions or whatever, we should.
Well, I kind of, that's kind of everything that I had that I wanted to just cover off the top of my head. We had some new guys that came in after we started, but you guys have DSMs? Cool,
Oh,
over
yeah.
here.
I have a 91 and a 95.
91 and 95.
We
Wait,
got 95 and 96
Good.
and 91.
good, you nice collection going. Yeah.
91.
91, all right. You guys down there? And you got too many.
Yeah, I got Formula One.
Yeah, Tom Dawes, yeah. You guys DSMers down there too?
Yeah,
Cool, 98? Yeah, cool. So who has just a general question like, hey, well you said this, but I think that's wrong, or something, just hit me with something. Who's got something, go ahead.
So like for your turbochargers, you have like some kind of like oil recommendation on like what type of oil to run, and I noticed in the charts it's always like zinc content and phosphorus. Is there anything else important in those oils, or is it really just the zinc and phosphorus?
When it comes to that's a great question. So the question there was like, I do have a document where I recommend certain types of oils and viscosities, and I say these are good and these are not good, and that's a document that's like 12 years old now. Actually, I probably ought to update that with some current products. But thanks for that question. So the ZDDP is really the bottom line on that, and that's what I was really going for with that document, was to direct people to oils that contain high levels of zinc and phosphorus, ZDDP additive. Because when you launch a car, of course, if you're doing a real good job, gravity is kind of at a 45 or a 60-degree angle for you going backwards when you launch the car. So all that oil goes up in the back of the pan, except for you ballers with the dry sump systems, okay? But all that oil goes up in the back of the pan, and you're on the two-step for 3 seconds, so a third of your oil's in the valve cover and hasn't come down yet, 2/3 is in the pan, and then you just hit it with 2 Gs of 1 G and 1 G, so most of your oil is at a 45-degree angle on the back side of the pan at this point. And you'll suck some air. A lot of time you'll suck some air. If you've got a good enough tire on there and you're cutting a 60-foot close enough, tight enough, you will suck air when you do that. What happens to oil pressure when you suck air at the pickup? It gets foamy, okay? So you can sink a boat by having a methane plume come up out of the ocean and have bubbles under the boat instead of water. The boat will just go right down into the bubbles, man. So in floating a bearing is the same thing, okay? We are keeping the thrust bearing, the thrust collar that's rotating away from the thrust bearing by having a pressurized oil film there. That collar floats on that pressurized oil. There's little ramps in there. The turbo's spinning, so you get some hydraulic pressure created because of the structure of the ramps. Okay, it's actually called a ramp bearing. You go look it up and read books and books and books about it. So you make some oil pressure in the bearing itself, but you need to bring some oil pressure to the bearing to get things started. So if you don't have enough oil pressure at the thrust bearing, you will have the thrust collar touch the thrust bearing. Now, this is where the zinc and the ZDDP comes in, because it's only going to happen very briefly. It'll be a 1/10 of a second or a few hundredths of a second that it happens, that the foam is going through there. But the surface speeds are crazy, man. If you got a 100,000 RPM turbocharger and you got the collar is, a 3/4 inch in diameter, do a little math there. That's miles per hour. That's a lot of miles per hour on the surface speed of that. And so if you take the oil away while that surface speed is there, and now the two pieces touch, it's like that air hockey game you used to play when you were a kid. I don't know if people still play that anymore. But if you turn the air pump off while the puck's sliding across that, it doesn't slide anywhere. It goes. Well, imagine the puck being at 150 mile an hour, with 50 pounds of thrust load on it. The puck's gonna light on fire, and that's what happens to the thrust bearing, So, but what can help that? ZDDP. because ZDP is a high pressure molecular component to the oil. It's not just it's not part of the dynamic floating thing. It's just when the film's gone and the two pieces are going to rub each other, what happens to be between the two pieces? The zinc and the phosphate, hopefully. They act like a little lubricant, like a little dry foam lubricant. It's an additive to the oil. It's not part of the oil necessarily. It has to be distributed in the oil, and that's all that's left there to protect you. So the oil recommendations basically come down to ZDP content. I like to add the oil recommendations also that the current trend of running 030 and 530 oil in everything is terrible for turbochargers. It really is terrible for turbochargers. We've recently done some oil pressure testing and analysis on EJ engines. Okay. And stock
You were able to keep it running long enough to evaluate anything else?
Yes.
Okay.
Through very judicious efforts and the help of Howard at RFAB, Darnice there. He helped us with the short block and the heads on that, and answered a lot of dumb questions for me. It was the first Subaru build I ever did. But we have in that application. This goes back to talking about oil recommendations and stuff. That application, we put the oil feed line we've been selling for years, which replaces a factory oil feed line that has a couple little restrictor orifices in it. So we take the line out that has restrictor orifices in it. You delete the little filter baskets in the banjo bolts because they can collect carbon and whatnot, cut down the oil. And you replace that with a dashboard braided line that we would sell. So with that, with our existing line kit on it, you get the car heat soaked to 210 degrees, and that oil pressure at the turbo would be between 3 and 5 pounds of oil pressure at idle. And you rev it up and hold it at 4,000 RPM and it go up to like 16 pounds?
Yeah.
16, 18
13,
pounds?
16
Yeah, yeah. And so I'm like, wow, that's not great. You know, and I start talking to some of my Subaru friends and I'm like, how come nobody's ever pointed this out to me before on these motors? And they're like, what are you talking about?
Nobody's ever measured.
Subaru doesn't come with an oil pressure sensor. Nobody knows. Nobody knows unless you add a standalone and you add a sensor into it. You don't know. There's an idiot sensor on it, and that idiot sensor was
So it triggers at like 4
PSI.
You have to have almost nothing.
Okay, so it's not a warning light as much as it is a call the tow truck light.
Right.
You know, so you don't ever know in a Subaru that you have such little oil pressure. The light's not even going to come on until you don't have oil pressure at all. So to help with that and to not have this problem, and you know, when we did the Dsm, we feed the oil off the oil filter housing with a dashboard line. We bring a lot of oil to the turbocharger. Turbocharger engine companies tend to have a higher priority. Motor companies tend to have a higher priority on losing the engine versus losing the turbo. So the turbo usually gets really low priority in the oil system. Usually it's at the very end. On the Dsm, it's at the very end. You feed the mains, the rods, you feed the camshaft journals, and at the end of the cylinder head, whatever's left over, the turbo can have. Yeah, that makes perfect sense, right? Turbo's not important. Why would we need to send a bunch of oil there? So years ago we realized this on Dsm. It's better to connect a line directly to the oil filter housing. Take the oil. You're not taking much. It's just a -4 line. So, but you're starting with a high pressure signal, 100 psi signal. So you can float the bearings, and that's just ended problems, oil problems on Dsms, unless you launch really hard. But that's a different story. So on the Subaru, I was like, let's set out to do the same thing. So I started looking at the oil galleys on the Subaru engine, and there's 2 plugs to the main galley on the top of the block. The first one has the idiot light in it, the 4 PSI switch light, and the second one's just a plug back there. And I'm like, well, dang, that looks good. So we took that plug out, and I made a fitting to put a -4 line on the rear plug. So now I've got priority for the turbocharger on the Subaru motor is after the mains and the rods, but before the heads. Okay, instead of mains and rods and also after heads. So putting a line there and changing to and not even changing oil, just keeping a 1030 oil in it or 530 oil in it. We doubled the oil pressure
15,
at
17
idle.
PSI.
Yeah. And then doing the line and then changing to a 1040 oil, oh heaven forbid, okay, made us idle at like 17 PSI, hot soaked. Okay, so we got 200 degree Fahrenheit oil, we got 210 degree Fahrenheit water, and we're sitting there idling with 17 pounds of oil pressure because we got a 1040 oil in it and we got the new line. And that's just gonna keep you from having turbocharger problems on the Subarus. That's a new product for this year, or for the beginning of next year. We're about to release it right now. But oil, that's a great question. Why ZDP? Because sometimes the oil's not there, and if it's just wet with oil, so hopefully that ZDP additive is still present on the surfaces, and it'll keep the surfaces from welding themselves together. It was a bigger problem in the past. We had steel on steel. We had steel thrust bearing and a steel collar. So a steel on steel bearing, steel bearing with a steel collar, really critical that you don't let the parts touch because they're the same material, okay? So they're stronger, it's a stronger bearing and it can hold its shape and deal with more abuse, but now it's kind of finicky when it comes to like being lubricated with bubbles. So ultimately went back to a bronze bearing because it was too much for a lot of people to keep up with. You know, could they find an oil that had a lot of zinc in it? You know, were they going to be beaten on it? Were they not going to be beaten on it? So backed off of the steel bearing and the benefits of the steel bearing, went back to bronze bearings just because they're less maintenance. They're not as picky and they're not as finicky. So that's where the ZDP come from.
Okay.
Who else would have another question? Yes, sir.
A question about altitude.
Altitude.
Base altitude's about 5,200. I live at 9,200.
Yeah.
There's an 8-mile stretch that is a serious grade on I-70. You run up that 120, that's 4 minutes, basically a lot.
Yeah.
How do you rate a turbo for that?
Okay, pressure, great question. How do you deal with altitude compensation? How do you deal with altitude? And what does that do to the turbo, especially if you operate at wide open throttle for an extended period while you're at altitude? If it's within the design parameters of the turbo, no problem. So if somebody thought about it ahead of time, like Dodge, say it's your tow truck, the engineers already planned for all that. There's an inlet pressure sensor, there's an outlet pressure sensor. The ECU knows what it wants for a pressure ratio. It knows what its limits are. It's going to stay inside those limits. If you didn't do all that engineering and you home built a race car to go up Pikes Peak with, then you're going to need to think about it. Mainly what you want to do is monitor what your inlet pressure for the compressor housing is versus the outlet pressure for the compressor housing. You look at those two in absolute numbers, whatever units you care for, kPa, PSI, whatever. You divide the absolute outlet pressure by the absolute inlet pressure, and that's your pressure ratio. You talk to your turbo guy and you go, hey, I seem to be operating at a pressure ratio of 3. Am I okay to operate at a pressure ratio of 3 to 1 at a flow rate of 60 pounds a minute? And then he'll give you your answer. You know, is that allowable? Is that overstressing or what? Another thing we do on Pikes Peak cars, and I do support a lot of Pikes Peak race cars, is we go back to the RPM limit. Okay, so on a Pikes Peak car where you want to be right at this edge, but you don't want to be here because you're falling. You want to be right here, just an inch back from the edge. You would go to turbo speed-based boost control. So you will bring the turbo up to what its max speed, its max mechanical limited speed is, and you would keep it there, whether you're at 12,000 feet or whether you're at 4,000 feet. And what is going to happen is it's going to result in a variable boost pressure at the intake manifold. It's going to result in a variety of horsepowers available at different altitudes, but it's all going to be stable and planned for, and you're not going to exceed your design criteria of turbochargers.
Spent 135,000 miles in my
Yeah.
and I've turned it pink a lot.
Yeah. Well, see, if you stay inside your yard, though, you don't get eaten by the coyotes. So if you stay on the map, you don't break the turbo, basically. So it really kind of comes down to understanding what the limitations of the turbo are and planning to stay inside that fence.
Right, and the pressure ratio, one of the things that we talked about a long time ago, and most people don't even think about, is what's happening on that inlet side. If you got restriction
It's
on
overlooked
that,
a lot.
Yeah, if you have restriction on that inlet side,
Yeah.
it's making that turbocharger work a lot harder to get to where you need to be.
And you think you're at 25 PSI boost, but the turbo thinks it's at 40.
Yeah.
You know?
So
And
clogged
you got
air filters.
you got the
yeah.
exhaust manifold pressure that goes along with 40 PSI too.
Mhm.
So a lot of times people go, wow, my exhaust pressure versus my boost pressure is really out of whack. And I'm like, well, it shouldn't be. I'm really familiar with this turbocharger running on a bunch of motors. Well, I measured it. This is what it's doing. I said, man, I'm not calling you a liar. I'm sure you're observing the world correctly, you know, but there's a reason for it. and you need to find it. And sometimes it's an inlet restriction. Sometimes it can be an outlet restriction on the turbine. So you can have a flex section, or maybe you didn't realize that you loaned the car to somebody and they drove over a boulder and pinched the exhaust pipe shut. If you've got 15 pounds of pressure in your downpipe and the turbo wants to have 30 pounds of drive pressure at the turbine inlet, guess what that means? You got to have 45 pounds of turbine inlet pressure in order to get 30 pounds of drop across the turbine to put the required amount of work on the shaft. So any downpipe pressure that exists just adds to EMAP. Any inlet restriction that exists adds to your pressure ratio. You're paying in cash for both of those things, right off the top of your dyno sheet.
Yep.
Paid for. Well, that's a good question. Who's got another question? Yes, sir.
So we were talking earlier about how large manufacturers didn't really care that much about turbochargers. I feel like in the last couple of years that's kind of changed. Mitsubishi with the 10th gen Civic making the 500
Yes.
horsepower or whatever. You've got Warner making the EFR turbos. What's some of the really exciting technologies that are coming out that are brand new that really excite you these days?
I tell you what gets me excited about new turbochargers is that we're going to better and better alloys on exhaust housings almost unilaterally. Like Mitsubishi does the turbochargers for the McLaren 720s, for example, and the 3.8 liter earlier models also. So Mitsubishi has a contract for both of those. Those turbine housings are made at one foundry in Japan, and this foundry specializes in cast steel divided housings, and really intricate cast steel housing. So I love seeing that all these new manufacturers with sophisticated turbocharger systems are embracing these higher alloys that tolerate these higher EGTs better. And I like seeing the shift towards solenoid controls wastegate actuators rather than pneumatic actuators. Most of the newer model cars will have an electric solenoid, a motor for the linear motor for the flapper valve instead of a pneumatic one. And that really opens up a lot of neat strategies for control, because not only do you know if you're trying to say I want more or less, but you also know the position that the valve's at. A lot of times on a pneumatic wastegate, you go, well, I got the boost controller cranked up all the way, but you're like, is the gate still opening? I don't know. It's making 800 horsepower. It's fire spitting out of it. It's loud. I can't tell you if the wastegate's open or not. But if it's in your ECU and you know that the wastegate position is 33%, well, that's how much it's open. It's open 33%.
Okay, I got a quiz question for everyone here, and I'm going to ask you, and if you think the answer is yes, I want you to raise your hand. When the wastegate opens on your turbocharger system, does your exhaust back pressure go up or go down? If you think it goes up, raise your hand. The wastegate's open, controlling the boost. Does your exhaust back pressure go up or does it go down?
Where are you measuring that, in the manifold or?
You're measuring in the manifold exhaust. I think it goes up. How many people think it goes up? Anyone else? You're all wrong.
Trick question.
It goes down.
You changed it to manifold, I was like, I don't
Yeah.
know. It'll up in the exhaust, right?
You're
So
really
Pressure will go up in the exhaust?
Before the turbo, your pressure will actually go up, because when you open the wastegate, now your shaft speed went down. So now you're getting less flow through the shaft. You're getting more through a wastegate, but less through the shaft. And you'll notice when you look at your data log, oh, my wastegate just opened here because I just saw my exhaust manifold back pressure go up. So it's one of those things you don't think about. So one of the things you can do, if you have the best match turbo is the one that never needs the wastegate open.
Free flow.
Yeah. So that is kind of your best situation. And one of the things a lot of people do, because of the advent of the 4-port boost control solenoid, they think, oh, I can get away. I'll put a 6-pound spring in there and I'll run 30 pounds of boost, and you can. And maybe that's something you could do or might have to do on a front-wheel drive where you don't have the traction and you need that wide range. But it's also a way to throw away just loads of mid-range torque. If you know your minimum boost you're going to run is 20 pounds, put a 20-pound spring in there, and boost control above and beyond. Do you disagree, or?
No, I don't disagree at all. And trying to use a sophisticated CO2, low spring pressure, multi-port solenoid and everything is definitely like grad school sort of approach to boost control. You know, the old rule of thumb is like, you know, if I use a standard interrupt style manual boost controller, and I've got a 10-pound spring, I can make 20 pounds of boost. That's a great rule of thumb to stick with. You know, so if your target is 30 psi, I like to put a 20 or 25-pound spring in there and have 5 psi of control. That way you got a lot of spring authority. You're not missing the mid-range because weak, it might be opening early. You put a 6 psi spring in there and you're trying to deal with duty cycle and send CO2 to the top of it, you may or may not be doing a good job of that. You know, so you may or may not be doing a good job of that. Did that answer the question? Yeah. Okay.
Yes.
I actually want to add to that a little bit, something really interesting that, yeah, if it's a really soft wastegate spring, the exhaust pulses can knock it open a little
That's
bit.
excellent. That's an excellent point to make. And if you put a linear position sensor on the wastegate, you'll see that.
Yeah.
You'll see that. And even though you have CO2 in there, the valve is moving a lot, okay, because the spring authority is not there. And the damping is only from the CO2 gas, okay, that you're adding to it. So it's not very well damped. It's a light spring, so it can be very excitable. And people go, well, why did I wear that wastegate out? It's only 2 years old, but the guide's all floppy and the valve has all the coating wore off and everything. Well, because you had a CO2 system on there, you had a light spring, and you're running a 50 hertz control signal to it. So 50 times a second, it's actually, since they're wiggling the whole dang time. It's not just out of position. Electric control, I want it at 33% open, and it just goes 33% open. It sits right there. It doesn't wear the parts out. You see, like a BMW 335 boost control in those is a vacuum solenoid, a vacuum actuator instead of a boost actuator. So the actuators on those are not normal, okay, in a sense. So there's a lot of activity on those, and you see a lot of 335s. One of the failure modes on the factory turbos is that they actually just wear out the bushing on the flapper arm for the housing. It gets all rattly, and so it starts leaking out of there, and it turns it's one of the wear locations on those turbochargers for sure.
And don't feel bad for missing that question. I thought the same thing until I just logged it. And that's the thing, the more data you can log, you can get a much better matched turbo for your project if you can give the manufacturer these specs. This is what I'm doing, this is what I'm seeing, and this is where I want to go. It takes 2 points to create a line, and that's it. And if you have those 2 points, you can get real damn close.
Yeah, you can. Another thing to remember about EMAP is that as you're driving the turbocharger to a higher and higher speed, you're consistently going to have to increase the drive pressure to do that. So it's not. A lot of people go, well, what was the back pressure? Where? Right before I shifted, or at the beginning of the next gear? Because they're going to be different. You're going to have lower EMAP at the beginning of the next gear because you have lower shaft speed to deliver that amount of mass flow. You're gonna, at peak RPM, when you're near the max RPM of the turbo and the engine, it's going to take an enormous amount of EMAP. So the EMAP, you look at EMAP, and it'll steadily rise. Well, you have all the flat boost pressure. EMAP will generally have a slope, an upward slope to it, and you'll have a peak in EMAP near your engine RPM max.
Yes.
Who's got another question? Yeah, yes, sir.
Not so much a question, but could you tell us a little bit about your time that you went MHI in Japan and studied with their engineers?
What a fun trip! Yeah, that was a fun trip. I on that trip I kept saying, well, I'm going to come back. I'm going to come back over time. I never went back over, but that was fun because we had Mitsubishi was kind of considering. I didn't really realize how much they were considering it, but they were considering doing more aftermarket stuff like they had done in the late '90s, and they had some performance turbochargers. They got involved with Reddy into the T78 and some 18Gs and 20Gs and stuff like that. But I was buying a lot of stuff from Mitsubishi, a lot of turbine housings. I still use a lot of genuine MHI turbine housings because, like I said, I'm really partial to the foundry they use, and I'm really partial to the quality of their divided turbine housings. That's unparalleled. The copies that you see on eBay and that some people use are garbage. I would never use them. I almost burnt my test stand down one time when one of them just melted a big hole in the side of it during a test. So MHI, they're looking at performance turbochargers, and I'm buying a lot of parts from them. And so I have a dialogue with them, on a regular basis. And they said, hey, we're interested in making an Evo 10 upgrade turbocharger. If we were to make an Evo 10 upgrade turbocharger, would that be something you'd be interested in buying from us? And I said, well, I'm kind of, you know, it was at the beginning of the Evo 10. It was, you know, 2008, I guess, first year in Evo 10. So this was like 11 or 12 when I ended up going, and it was like 10 or 11 when they started talking about it. And they said, well, hey, if we did this, would you be interested? And I was like, absolutely, because you know, it's a lot of trouble to build these custom things, and if you guys had a box turbo that a lot of people could use, I'd be happy to sell it. And they said, okay, well, what we'd like to do is we'd like to check out a couple of models that you make for the Evo 9 right now, because we really like what we see about your green model and your red model, and we want to kind of make something that's kind of in that range for the Evo 10. And I said, well, I was jokingly, I was like, well, yeah, heck, I'll build a couple and I'll fly over there with them and we can put them on the test stand. And they were like, yeah, you bet, sure. And I was like,
yeah. Just so you know, getting access to a test stand is next to impossible.
You know, and so I ended up having a great trip. I mean, I was like a guest of honor. I was eating dinner with these, you know, MHI engineers and the directors of aftermarket turbo and stuff. It was a great trip, and I didn't realize how serious they take turbochargers. But like just about everything in a Japanese sense, they take everything really seriously. So I mean, like the test cell that they test burst in, okay, you got to realize they make turbos for ships too. So they got test cells for cars, car turbochargers. They got test cells for ship turbos that you can't wrap your arms around the compressor wheels on. So we're looking at one of these containment test cells, and I walk into it, and it's like a big walk-in oven, man. It's got steel plated walls, and it's like 2 foot thick concrete, reinforced concrete all the way around it, and a great big like vault door like you have at a bank, you know. And so we walk in there, and I'm like, this is really eerie. It's a really eerie feeling, and you can see these scars on the walls, you know, for you know,
those class limit turbos.
Yeah, basically, yeah. And so I was like, wow, it's kind of overkill. And they're like, no, it's not overkill. You know, you have to run these things. You have to watch them explode. You have to know exactly where the limit's at, and you can't just do it all by calculating. You got to calculate, but then you got to verify that you're right about things, and then you got to learn what really happened and learn what you didn't know about why it was breaking. So the test cells over there was just the most awesome thing about that, the testing, and I was so proud of our product. We got over there, and they're running the speed line. So you run one RPM at a bunch of different flow rates, and you collect all these points. You just keep going in. And they're like, okay, we're at the end. And I was like, I got to sit there and watch it. It took hours. And they're like, okay, we're at the end. And I'm like, no, there's like 2 more speed lines. And they're like, no, we can't run them. We can't run them any higher than that because they'll have bearing failures. And if it fails, it's very expensive to clean the oil out of the whole test cell, because it's, you know, it's got 50 yards of pipes and tubes and everything. I mean, it's in a room almost this size, and the turbo's just in one spot. There's all this equipment and valving and stuff. And they're like, no, we can't do it because, you know, if it breaks, it's really difficult to clean. I said, man, I know those other 2 RPM lines are there. I promise you, it's not going to break. And they were looking at me, they're like, really? And I was like, yeah, it's not journal bearing turbocharger. It doesn't have this thrust limitation. And they were like, okay, we'll do another line then. They did another line. They're like, wow, that's nice. You know, and it was so flattering to me to go there and talk to those engineers and have them test my thing and go, that's some very nice turbos you have there, you know. And then they tested our green and red model, and you know, I've got compressor maps from our turbochargers at Mitsubishi in Nagasaki. It was awesome. It was awesome. That was an awesome trip. And then so they took those 2, the green and the red, and they were like, you know, hey, I think we use this. We need to use this turbo wheel. I was like, what the heck turbo wheel is that? They're like, oh, that's one you hadn't seen before. We just pull it out. Like it's like halfway between a TD05H and a TD06H. And I was like, it's only got 9 blades. They're like, yeah, it's a very nice turbo wheel. Where do you guys get this stuff? They're like, we have thousands of turbo wheels. I had no idea, you know, because we just don't see them in everything. Yeah. You know, they have a wide variety of parts that you just never will even see. So they made that 54 millimeter X-Deucer 9-blade turbine wheel. They didn't make it for this project. They already had it for some industrial project, but they matched that with that 18 GK3 compressor, which is a really nice 55 or so pound a minute compressor. And then also they made a new thrust bearing. because I was explaining to them how when I build the journal bearing versions of it, I don't use the factory thrust bearing because I use a larger diameter one, and they were like, well, you made yours too big. And I was like, I'm all ears, buddy. You tell me what I did wrong. I'm all ears. And they're like, well, it doesn't need to be that big on that side, and this side we could pull it in a little bit. And I was like, man, if you guys say so, that's fine with me. So now there's a new intermediate thrust bearing. It's not the one that I made in the late '90s that you see on eBay right now. The monster thrust bearing. It's not that one, but it's an intermediate one that doesn't have as much drag. See, they're really sensitive to things like that, parasitic losses. They're really sensitive to noise, vibrations,
and noise
harmonics.
itself too.
Yeah,
that was the funny part.
One of the things I was asking them about compressor wheels is they had this display on the wall with about 30 different compressor wheels in it.
Stop. There we go.
So they had a display on the wall with about 30 different compressor wheels in it, and I was like, I didn't know there were all those different eras, because they, out of a 20, out of an 18 or a 20 size, there was like 14 different wheels, and it was like a G, a T, a TK, a GK, a GK3, a DKG3, and I was like, what are all these for? Oh my God, I didn't even know all those existed. And they were like, well, sometimes Mercedes or Honda or somebody else, they'll want it to be quieter. They want the compressor to be quieter. And I'm like, you would entertain the thought of that? They're like, well, if we want the contract, we have to make it quieter, right? So we want to sell them 500,000 turbochargers, so we rework the compressor wheel and we come up with a TK3L version that is quieter. And I'm like, wow, it's just an amazing amount of engineering you guys do to get these contracts and stuff. But that's why they don't care about aftermarket so much, because they want one customer, they want to sell 1 million turbochargers to them over 3 years. So aftermarket, we're just not going to buy that many 16Gs. So we're not that important compared to Mercedes. So I realized that, and I was like, man, my guys love how loud my compressor is. We call it the audible tachometer. It's an audible RPM indicator. If it's spooling or not. And they all laughed, and then we ate sushi. So that was a fun trip. It was a lot of fun in a lot of ways, and I'd never been to Japan before, which is a whole experience in itself. And you guys like the idea of going to Japan. You had to talk to Mike about it. Mike's
we've
got
been
a great
going
program
since,
for that.
We had a program since 1998 putting together a Tokyo Auto Salon tour. And if you guys have never been to Japan or thought about it and you want to be able to go over there and see some cool stuff, definitely join us on the tour. I think next year it's mid-January we leave. We leave on a Tuesday, we get back on the following Wednesday. But we'll go out there, we'll tour the Nissan factory where they have their collection of all their cool cars. We'll go to the Tokyo Auto Salon show. We'll go to a bunch of different places. We'll go to the all-you-can-drink, all-you-can-eat place a few nights, the izakaya experience. It's just a blast. And the cool thing is, after you go on that tour once, you're comfortable enough that you can get around in Tokyo on your own if you ever need to go again. So
I would recommend the first time you go to do something like this, where you have some scheduled activities and a guide, because otherwise Japan's not the same as America. They're not we're inclusive to the part where we'll cut our own leg off to be inclusive. Japan is a lot different social environment. They're not scared to say they're nationalists. If you're a Japanese person, you live in Japan, it's okay to be pro-Japan. We don't have the same problem we have. You can't be pro-America and be an American and be proud American. It's bad. But in Japan, you can be a Japanese guy and you can be proud to be a Japanese guy, and it's good. Okay, but you don't see English everywhere. If you need to get around by yourself and you don't have anybody with you that can talk, it can be kind of a challenge. I had to take a couple of buses and a train to get to the airport on the last day, and the guide guy was like, okay, say it back to me again. I said it back to him, all the steps of where I was going to go, and he showed me where they were. He's like, okay, you're going to be fine. Right. I was still nervous. I was still so scared because it's so weird to not be able to communicate. So that's why I'd highly recommend the D-Sport trip, because you get guided around. The communication won't be as much of a problem. But I really recommend going. It's so beautiful, and the car culture there is really cool. I guess it's kind of diminished a lot.
The car culture is definitely diminished. Tokyo it's a city that's not built for cars, you know?
Right.
It costs so much money to own a car. If somebody owns a car and they live in Tokyo, they really love cars. Even if it's just a K
And
car.
if you're
or
getting
whatever.
around in there, you'll realize why you don't need a 800 horsepower car. There's
Yeah.
not any place you can do anything with
Yeah,
it. you know?
but going outside of Tokyo or going to Osaka and doing all this other stuff, you can see more of that. But we've gone to different factories. Like we'll go to Greddy one year, or we'll go to Mines, or we'll go to Tomei and stuff, and you get to see stuff there. But it's really cool. You guys have a great time, and we just did our 20th anniversary edition of D Sport. And if you're a racer, go by, pick up a free copy at the booth. And we had a bunch of employees over the last 20 years, and we reached out to some of them, and I'd say at least half of them, their fondest memories are Tokyo. Things that happened in Tokyo or things that we got to do. So definitely, if you guys have an opportunity, we're gonna probably have about 40 people next year. The yen is really, the dollar's really strong. So if we go to all the parts garages and stuff, you can probably get some good bargains and stuff like that. Food will be cheap. Souvenirs will be cheap. So it's a good time to go.
So on that real quick, with the whole COVID thing, how's the restrictions on that?
So right now, they keep lowering the level. Right now, you don't need a PCR test or anything if you have, what is it? I think you have to be vaccinated to avoid that. Now, if you're not vaccinated, you have to take additional tests. So it could delay you. But if you have...
But there was a quarantine requirement that recently came off.
That's the one that came off, yeah.
So
So
you have to go there and then sit in a hotel for days.
No, you don't have to do any of that.
Yeah.
So
But
now
it depends on what
stay
you're...
longer?
What's that?
So now we can't stay longer because of that?
Yeah.
Well, your trip instead of having 6 days of quarantine in it has 6 days of trip in it.
Yeah.
Yeah. You guys that came in later have any other questions or anything before we wrap this up? I don't really have anything else to add unless there's some other questions and topics I can talk
Yeah.
about.
I have a question.
Yeah.
Can you tell me a little bit more about your Zona turbine wheel? From the looks of it, it looks like something that you would do back in '90s of clipping the turbine
The
wheel.
UHF.
Yeah, UHF. Yeah,
So
six turbines.
is this like the clip wheel taken to the next level in Zona?
Yeah, it's kind of a thoughtful, more academically correct way to achieve what you're trying to achieve with clipping. It doesn't kill all the efficiency of the turbine wheel. It actually, instead of having efficiency humps that are very narrow like this, like you have with a normal turbine, a standard full blade turbine wheel, they're wider. So you have a wider mass flow rate for each efficiency island that's in it. So it basically takes the efficiency of the turbine and it kind of stretches it out. So it's easier to get speed matches. What's a speed match? That's when the compressor wheel gets to run at an RPM that it really likes, and the turbine wheel gets to run at an RPM it really likes. When you build a turbo where you've got both sides running at the RPM that both sides prefer, it wins. That's how you get that 0.8 EMAP to MAP ratio, where you got 30 pounds of EMAP and 40 pounds of boost. You've done a really good job speed matching. You've done a really good job with your efficiencies if you can achieve something like that. And UHF makes it easier to get that because the efficiency islands of the UHF are wider. So you're a little off the peak, but that's okay because the peak it wasn't the Himalayan mountain. It was just like a mound. So you're a little bit off of the perfect spot, but being a little bit off didn't hurt you as bad as it would have in other turbine wheels. But the key thing about the UHF and why it's useful and an improvement is that it lets you have a low inertia turbine that has a lot of inducer area. That's the inducer tips where the air first touches the turbine. It lets you have a lot of inducer area, but not a lot of blockage area in the outlet part of it. So you're reducing inertia, you're increasing choke flow. At the same time, you upped your blade count, and you have more inducer paddles to do shaft acceleration with. So it's just everything that a UHF does is a good thing. And that's one of the reasons it works so well. And there's more to it than just like, hey, we need a turbine that's got an even number of blades, and we're going to take half of each blade off. It looks like that's what it is, but there's
little bit more arrow
There's
to
a
it.
little bit more to it than that, yeah. So, but thanks for asking that. But the UHF is a great way to increase choke flow, increase shaft acceleration, and increase the likelihood that you're gonna have a great speed match with your compressor.
And from a manufacturing standpoint, it's better for you because you don't have to have 12 turbine wheels to cover 12 compressor wheels. You can.
If we were smart, we wouldn't have 12 turbines.
Right.
But we're not smart, so we do have a bunch of different
Oh, do you?
sizes. Yeah, that's a 46 millimeter extruder, a 51, a 57, a 64, and a 69 millimeter extruder. So that a whole range of small frame turbochargers. There's like 5 different turbine wheels you can pick for that range. So you really can't tailor it. And sometimes, like one of the autocross cars, the 1G autocross max effort car with the wing on the back, 57-pound compressor with a small 51S turbine on it. So it's kind of heavy load turbine, but it works awesome. He loves it.
I have a follow-up question because I know it's increasing the choke flow because of that, lesser blade on an even odd, and you keep an inertia low, which is going to help the spool. But would there be ever a consideration of adding some kind of like divided, like a turbine housing to kind of take the spool on the spool side a little bit better to come up?
Well, divided housing, you're kind of asking a divided housing question. As far as how does that help spool? It can, especially below 4,000 RPM. A divided housing can really help with spool on a 4-cylinder engine below 4,000 RPM. By the time you get past 4,000 RPM, though, the pulse frequency on a 4-cylinder is so high that the pulses are not really there anymore. If you start watching the pulses at below 4,000 RPM, the pulses are there and you can see them. So trying to harness the pulse energy, there's some gold in them Bower Hills. Okay, but once you get past 4,000 RPM, the pulses are so frequent that seeing the pulses is hard. So trying to make any money on them is going to be hard too. Okay, why aren't there divided turbine housings for Zona rotor small frame turbochargers? Because they're not for tractors. You get a 14-pound T4 divided iron housing. That's just not what the Zona rotor thing was trying to do. So the Zona rotor stuff is we like a nitronic or a high grade stainless turbine housing for that, for safety, for lightweight. You generally can, and also on the UHF, you get to really come down one AR size from where you were. So like say you had a 68 millimeter Zona rotor with a 68 millimeter turbine wheel in it, and you're running a 103 turbine housing on it. When you go to 69S, you get to run an 82 turbine housing. So it helps shaft acceleration even more, okay? But you still don't choke flow because of the turbine being the UHF design. So it's kind of a new card. It's kind of a new thing to play with as far as sizing and speed matching and turbine housing selection. But one of the big things that I didn't mention, and I should have said about UHF, is you get to run one size smaller AR in a lot of cases. We got guys out there running 105, 105 pound a minute, 72 millimeter inducer, 69S, they get 1,000 horsepower with 82 AR turbine housings and having wide power band. So, that's a good question, turbine housings. We'll probably end up making some divided turbine housings at some point, but there's so many other parts to make right now, and we're not a multinational billion-dollar company. We're a small made in America kind of company, and we cast all those housings in Michigan at the tile plant. So we have some manufacturing limitations on volume and cost and things like that. We're just not ready to outsource any of that yet. So, anybody another question? No? Man, thank y'all so much for listening to me talk today. I really appreciate it. I always enjoy coming and talking about these things. It's always a good time. Always good to see you guys. Some of you guys came in late. You didn't get in on all of my koozie throwing and t-shirt throwing and stuff like that. Come by my booth and see me. I'll make you a deal on some t-shirts and give you a t-shirt and stuff like that. Also, I got Dsm Manifolds on sale. $150 for a Dsm manifold. The cast manifold is an example of it right here. I'm not sure what the regular price is on that, but that's $100 off or something like that. We got Speevo 9 cast iron manifolds here. Those are on sale for the event. I don't have very many of them. I think I have like 3 or 4 of them. Those are on sale for $200 a piece, and that's almost $100 off or something on those too. And I have someone with me, and I do not want to take them back to Texas. So if you're in the market for a cast iron manifold, come by and see me. I'll probably be desperate tomorrow afternoon. So if you're trying to try to lowball me tomorrow afternoon about lunchtime, it'd be a great time. Come around, lowball me on some display merchandise. Yeah. So with all that said, I will wrap that up. Thank you so much. Thank you.